Okay, let's begin. Welcome back. It's week 2. It's a Monday, and I left this slide last time for the beginning of this time. This is the summary slide for the sets. It has everything that we have gone over. Not everything from MACM 101, but most of the things. The only thing of worth that we haven't done is how many k-element subsets are there of an n-element set. We're going to deal with that for combinatorics, although we sort of know the punchline there is n choose k. Okay, but we'll develop that a little bit later. Anyway, the example here has a lot of stuff for you to do, and some of you came in a couple of minutes early and started filling in the stuff that's marked in red as mainly the stuff you need to do. Anyway, let's just go through it. Okay, so all the terminology is here within 3 sets here. There's A and B, and they're sort of defined longhand like this. You can also, do set builder for, these are sort of like weekend days or all X such that this is your favorite day or something. Maybe I'm being presumptuous about that. These are classroom days, for Compute 210 days. They might actually be your favorite days because, Compute 210. Sorry, days of week. Okay, but we could use like set builder, all Y such that Y is a day we need for Compute 210, and so on. Anyway, S, our universe, our grand set is all the days of the week: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And we have membership. This little E symbol or an E with a cross through it denotes membership. Monday's in A, Thursday's not in B, Thursday's also not in A. Cardinality denotes set size, and the size of S is 7 days in a week. Size of A and B are both the same. They're 3. And there's the empty set. There's nothing to quiz you about here, but that's our symbol for the empty set, a special case where there are no elements. Doesn't come up very much in this course, but occasionally. Subset, everything that's in A is also in S. Other things that you also know, A is not a subset of B. Okay, there is some overlap, but there are a couple elements of A that are not contained in B. And you can also say something in general about the special sets, the empty set and S. The empty set is a subset of every set, and every set is a subset of S. Okay, so for every set A, the empty set is a subset of A. A is a subset of the universal set, the universe set S, and A is also a subset of itself. So I'm just going to mention that while I'm in there too. Okay, so I know it seems a little bit trivial, but sometimes you need these things. Okay, proper subset means that there's a difference between them, and A is a proper subset of S in this case. There are actually 4 examples of things that are in S that aren't in A, and then we get to our exercise portion. Okay, so hopefully you've had a chance to fill these things in. I'll do a few of them, and I'll ask you for help on a few of them. Okay, so A bar, everything that's not in A, so that would be Tuesday, Thursday, Saturday, and Sunday. Okay, so 4 things. Union, that's everything that's in either one or both, so Monday, Wednesday, and just to be confusing, I'm going to sort of do it in some odd order, because, we don't really care about what order they come in, even though it's a little hard on the eyes. This is a perfectly valid way of expressing this, okay, so just be aware. Intersect, there's only one day that overlaps your favorite days with Compute 210, and that's Friday. Okay, let's turn it over to you for the last few here. Set difference, A minus B. What's in A minus B, please? Say that again? Monday and Wednesday, good. The overlap is subtracted off. You get disjoint sets when what occurs? Okay, probably more than just that. No, that's not it. Yeah, so A intersect B is empty. I think the problem with yours is that you need both things. You need both directions, yeah. So you need, you said an implication. If X is in A, it's not in B, but you also need it the other way around. Partition, what do you need for a partition for, like if A and B were a partition of this set, what would you need for that? Okay, so what does that mean algebraically? A union B is S, good. And we need one more thing. And they're disjoint. Good. Last, the size of A union B, we could actually compute that using just what's up here and say there are 5, but I want to use the inclusion-exclusion rule. Okay, so that's when it's the size of A plus the size of B minus the size of their overlap. And we can compute those also by going up here, right? So there's a 3 and a 3 and a 1. So 3 plus 3 minus 1 is 5. Okay, so hopefully you got all those, and we can feel pretty confident about our set theory stuff, right? Maybe not super confident, but you're going to do a couple exercises, and please don't take photos. Okay, I saw you, and I saw you. Okay, so this is your final warning about taking photos. Okay, so I made a big slide about this, and I talked about this on day 1. Okay, so I have a rule, and it's about the only thing I'm going to call you out on besides being like really disruptive. Don't take photos in this class. There's no need to. Okay, so take your notes. You have a question? Sorry, your hand isn't up. Your drink is up. Okay, any questions? Okay, so that'll be it for set theory until you have your assignment. That is good. All right, functions. Hopefully this, it shouldn't take the whole lecture for us to get through functions, okay, but we have to go through them nonetheless, okay? So the functions are usually seen as connective tissue between sets. Okay, so we need set theory to do functions. Okay, so what are the definitions? All right, first of all, let A and B be sets, and I color-coded them blue because we have lowercase a's and lowercase b's, and it's sort of hard to tell what's a variable and what's not, so anything that's a variable here should be blue. Anyway, A and B be sets. F is a function from A to B. A is like the from set, B is like the to set. Okay, so you're mapping elements from A to B, and the way that this goes is every element A, little a and A, is mapped onto exactly one B and B. Okay, it's possible that more things map onto the same B, okay, but only one thing in the A set, there's only one thing that each element in the A set is allowed to map onto. Okay, there's some notation. F colon A arrow B is a function that is not A implies B. I know it's the same looking arrow, but they mean different things in different contexts, and we say F maps A to B, or F is a function from A to B. And we're used to this notation, F bracket A equals B. We often say F of A. And we're used to it not just from math class, which we've been doing forever, but also computer science class, right? That is exactly the same function notation that you use for a defined function. When you want to call a defined function, you pass in parameter A, and it will spit out the value that it maps onto B. Okay. Anyway, B is the unique element of B related to A by function F. And this, sometimes we use quantified statements, right? So let's get that back in there. For every element A in A, there exists a unique, that exclamation point means unique, element B in B, for which F of A equals B. Okay, so that's what that statement says, or this is the definition of a function. That is the condition. Every single thing that's in A has a corresponding element it maps onto, and it's one and only one. Okay, this is the total function condition, and there are some weaker definition of functions that are out there where you're allowed to have a hole in the curve, like some sort of singularity. Not everything is defined. We're not going to deal with those. They're not very useful for us, but they do exist. Okay, you can't have two things. You can't map onto two things. There are a couple other things you need to know. B is known as the image. A is the pre-image. And we have the domain is the set A. This is the from set. Okay, so all elements come from there. The codomain is the to set. Okay, so everything is mapped to an element in B. Okay, example time. Okay, so this is just a very simple discrete example where we have 4 elements in the domain A, 1, 2, 3, 4, and 4 elements in the codomain B, Q, R, S, T, 4 letters. Now, if we were to map out this function using a Venn diagram, we could do that. Okay, so here we're going to put like a pool over here for A, and the elements in A are in no particular order except convenience. There are 4 dots somewhere in that set. And B is over here, right? So we have another Venn diagram, and it's got a set for B, and Q, R, S, T, right? And what does 1 map onto? Well, we have them all defined here, okay? So F of 1 is R, F of 2 is R, F of 3 is T, and F of 4 is Q. Okay, it's explicitly defined, and you can define a function that way. You can define it one element at a time. It's perfectly valid. Okay, so if we were to draw this pictorially, and I'll just make sure, we're saying, okay, F is connecting elements from A to B. Arrows will run from element to element according to this. F of 1 maps onto R. So here is an arrow going from 1 to R. F of 2 also goes to R. F of 3 goes to T. And F of 4 goes to Q. And I don't really want to cross lines, but hopefully this will be fine. Okay, so images. All of these things are images except for S. Okay, so let's see. Let's just do it by image count. So S is never an image. Q is an image once. T is also an image. Sorry, Q and T. Let's try that again. Q and T are images once. Sorry, I missed that. And R is an image twice. Okay, so that's the mapping as it is, and I think we had, right, the codomain and the domain. Okay, so this is the domain, this is the from set, and this is the codomain. This is the to set. Okay, so far so good. Okay, we're not quite done with this diagram, we'll come back. Yeah. Sorry? Is S included in the codomain? Yes, it's in the codomain, it's just never reached. Okay, so there's another term which we'll get to on the next slide, which everyone talks about in high school and sometimes late grade school. It's the range, and it's basically a collection of all the images. So it's perfectly valid for you not to be able to reach every single thing. Okay, but that's the difference between codomain and range. Thank you. All right, next slide. Okay, more terminology, and then we'll come back to the example and finish it off. All right, this talks about range. Okay, so good timely question there. Okay, the range of F is the collection of all the images that you can reach. Okay, this is often written as F of A, and it seems a little strange to say function of a set, but this is a shorthand notation for a set builder thing. So in general, if you have F of some set X, you are going to take every element of X and pump it into the function and collect all the images into the set. Okay, so using set builder notation, this would be all the images B such that B is equal to F of X and X is in X. Okay, so little x is an element of X. We just sub in all the things and collect them all into a set. Okay, so F of a set gives you a set of all images. F of A is the set of all the domain. Okay, so you get the subset of the codomain that it touches. Okay, so just going back to this slide for a moment. Okay, so F of A collects everything that's in here, S, Q. Oh, sorry, S is not, sorry, I did it in the wrong order. Q, T, and R. Okay, so S is not in there. S is the thing that's missing. Okay, some functions are special because of their range, and there are 3 of them, so let's do this. So if the range equals the codomain, that means it covers everything in the codomain. Okay, so range equals codomain, good stuff, everything is accounted for. Those are called surjective functions. And if I was to use quantifiers again, okay, so every possible image is accounted for, we would say that for every image B, or for everything in the codomain, there exists some pre-image in the domain such that if you sub it into the function, you get that image back. I'll put a red box around that, I'll put another red box around it. Okay, so thinking about in quantifiers, every possible element in the codomain has an A such that when you sub it into F, you get B. Okay, surjective function or onto function. Okay, let's look at the second one. Okay, in the second case, no image appears twice. Okay, so no image appears twice. That means that we don't have a situation, if we're looking at it diagrammatically, where there are 2 arrows pointing to the same item. Okay, so there must be a unique pre-image for each image. It's possible that you don't get an arrow going to every item. Okay, so it's not necessarily surjective. Okay, but if an item is pointed to, if there's an image, there's only one way to get there. That is known as injective or one-to-one. Okay, how would we state that thing using quantifiers? Well, basically, you could write it as like a negative statement. So you could say there do not exist elements X and Y in the domain where the 2 things are not equal and they lead to the same image. Okay, there don't exist 2 elements in the domain that point to the same thing. Okay, we could turn this thing around, and often when we deal with this in Macam or calculus, when you're asked to prove something is one-to-one, you'll do an alternate form of this. Okay, so you can actually distribute this negation through this quantifier, and it will flip the quantifier to be for every, and it will negate this sentence. Okay, you negate it, it becomes De Morgan's, and then you have an or in there, and then you can factor out the or and make an implication. This is pretty typical for everys. So you'll end up getting this statement. So if X is not equal to Y, then F of X is not equal to F of Y. Okay, so if we read that statement out, every pair of X and Y that we pick, if they're not the same, then they can't go to the same place. Okay, so that's another way of stating injective that seems to follow the definition. But you can also do the contrapositive of this. And in calculus, this is what you do in calculus. Okay, so for every xy that's in A, F of X equal to F of Y implies X equals Y. Okay, so if you're asked to prove something's one-to-one in calculus, that's pretty much what you did, is you said F of X equal to F of Y, and then you derived X is equal to Y. All of these things mean injective. All of them. Okay, come back to this in a sec. Let's go back to the example. Okay, so first things first, is F surjective? We are going to have a vote. Yeah, it's Monday, we should get a little stretching in, a little bit of activity. Yeah, you're going to vote. Okay, so we're going to figure out, is F surjective? Prepare to vote. Okay, you ready? Okay, let's vote. Who thinks F is surjective? Who thinks it's not? All right, that's good. Unanimous? Somebody prove to me that it's not. Good, yeah, S is never an image. Okay, so you need total coverage. Well, S isn't covered. Good. Okay, next question, is F injective? Prepare to vote. Okay, ready? All right, let's vote. Who thinks F is injective? Who thinks it's not? Okay, all but one voted for not injective. Prove it. Good, R has two preimages. Okay, so it is reached twice, it's pointed to twice. Okay, these are known as counterexamples, and if anyone ever asked you to disprove these things, remember it's A for every. You just need one counterexample to disprove the cause, right? Okay, so that's a very, very fast way of doing a disproof. Yeah. All right. Let's talk a little bit more. One more thing, bijective. Okay, if both surjective and injective, then the function is a bijection or a one-to-one correspondence. Now, there's one thing that you can do as far as, or you can conclude, pardon me, when you know something is surjective or you know something is injective. Okay, let's start with surjective. From a counting perspective, you know that one set is bigger than the other, or at least as big as the other, right? Which way does it go? Yeah, A's got to be at least as big, right? Because for everything that's in A, it's got to cover one thing in B. It might cover the same thing multiple times, but that's not helping our cause, right? Okay, so a surjective F is possible if and only if the size of A is at least the size of B. It could be equal, okay, but you need enough things to start the mapping. You need enough pre-images to get all the images, right? Injective is the opposite. Right? So for everything that's in set A, it's got to map onto something that's in set B that it can't, nothing else can map onto it, right? Okay, so we can't have extra things in A, right? Okay, so yeah, an injective one has the opposite effect. Okay, if the size of A is at most the size of B. Okay, otherwise, it's impossible for there to be an injection. Right? Bijective is both, which is interesting. You have the size of A is at least the size of B and at most the size of B, so therefore it's got to be equal. Okay, I saw a hand go up, so I'll just take the question while we have a moment. You still have the question? No? Okay. Any questions while we're paused? Good? Yeah. How A can be smaller than B? Yeah, I mean, definitely, like if you look at the previous example, right, A is at most B. We could have made an injective function. We could have just made 2 map onto S, say, and then we would have been fine. Yeah, so they can be the same size. You can imagine like A was just slightly smaller. Maybe it has only 1, 3, 4. Remove the 2. Then it's mapping onto 3 things over here, but it's not going to map onto all of them, right? So it is possible. But if we had 5 things over here and only 4 things over here, at least 2 things are going to map onto the same one, right? Yeah, it doesn't require surjection. I think that's a point of confusion. Yeah, it doesn't require both. Good? Yeah. Not continuous? Yeah, I mean, the continuous thing is interesting because, and we don't cover a lot of continuous stuff in, like we would in calculus. Just remember that the real numbers set, right, is very, very dense. So yeah, you can have different sets, like even infinite sets, like the natural numbers versus the integers. And even though the natural numbers are a subset of the integers, it looks like there's half as many there. It's actually the same infinity, and it's the bijection that connects them. So you actually find that there can be an equality between those two sets. There is a bijection. Okay, so that's actually the subject of the next slide. So this is good. Okay, so functions and counting problems. Okay, so if A and B are finite, and that's most of the cases we're going to deal with, there are some countably infinite things that we deal with, but not too many. If you find a bijection between them, that means they have the same size. Okay, that is a lot of what we do in combinatorics. Okay, so you're going to see some patterns of permutations and combinations, and you're going to apply those formulas by mapping the problem that you read onto a problem that you've seen before. More than that, a bijection, a function, basically a function count, if you find 2 different ways to count something, that bijection connects them, and it makes those 2 different things equal. It's actually known as a combinatorial proof. As an example of a combinatorial proof that's accessible to us, we're going to recycle an example we did on the first day of class. I know it's been a while. But we have a coin is tossed 10 times in a row. How many possible outcomes are there? Well, if you remember, we made a string of H's and T's, and the string was 10 long. Okay, so method 1 is to do that. Okay, so count the head-tail sequences of length 10. And we did that. There were 2 times 2 times 2 times 2 times, okay, or a permutation with replacement. Okay, we got 2 to the 10 ways. And we use that as our denominator. And that's not where I want to go with this. Okay, method 2 is to accumulate a bunch of cases, and we did sort of cases when we did the part B or part C or whatever of that example, except we're going to count all the cases, okay? So we're going to count the number of heads that appear, and we just counted like 3 through 7, but we can do all of them, right? So there would be 0 heads in, and it was 10 choose whatever, it's going to be 10 choose 0 ways, and 1 head in 10 choose 1 ways, and so on, and we'll just sort of do the ... because we only have so much time and so much ink. Okay, so 10 heads in 10 choose 10 ways. Okay, and there are 11 different items here. And they're all distinct. They're all like disjoint from each other anyway. Maybe not distinct, all disjoint from each other, which means that the rule of sum applies. Okay, so one way we just generate strings. Another way we count the number of heads 11 different ways. Okay, both ways count everything in the set exactly once. There's a bijection between these two things, so they must be equal. Okay, so the left-hand side is 2 to the 10, and the right-hand side is the sum 10 choose 0 plus 10 choose 1 plus 10 choose 2 plus 10 choose 3 plus all the way up to 10 choose 10. And that might not be obvious, right? It might not be obvious that the sum of the entire row, the 10th row of Pascal's triangle, is 2 to the 10, but it is. Okay, so it's kind of neat that something interesting like this will drop out of bijections. Yeah, nice. And this won't be the only combinatorial proof that we do, but anyway, you can do this. Okay, we're going to do one example, and it's an introduction of a common problem in this course. It's going to come up over and over again, including your first assignment. Okay, let's dig into it. I'll leave that out there because some of you are still writing. Okay, and it's counting functions. How many different functions are there of a certain type? Now, what is this function that we're counting? Well, it's some function, okay, that maps from A to B, where A is of size n and B is of size d. Okay, sometimes the variable letters are different depending on what problem you're doing, but this is known as balls in bins. So you can imagine taking n balls, and you have d bins. They're numbered 0 through d minus 1. As we deal with computer science, we're 0 indexed around here. Anyway, you toss all the balls into, each ball goes into a bin. Each ball maps onto a bin number, is basically what's happening. Okay, so you're developing a function, and you can ask a bunch of different questions about the distribution, like how many ways are there of having balls that go only, no ball has 2 bins, or sorry, no bin has 2 balls, what's the average size of, what's the variance of the size of, how many balls are in each bin, and so on. You can ask a lot of interesting questions, look at the distribution. It comes up a lot. Okay, today we're just gonna ask you how many different functions are possible. Okay, and we can do this, all right? So let's do it. Okay, first question is, how many functions from A to B are possible? And it's multiple choice because, again, we're all about voting here. Okay, so I'm going to give you 30 seconds to give it some thought, and then we're going to have a vote. Okay, so 30 seconds. All right, so 30 seconds. That was 30 seconds. Have you made your choice? Okay, I've noticed that a lot of you haven't participated in a vote, and there's no reason not to. In fact, I hate it when I'm wrong, and I put up my hand and I look silly. So, if you have no idea or you've narrowed it down to 2, vote twice. And then you'll be right. It's all cool. Vote 5 times. Okay, I want you to vote at least once. Okay, this is what it comes down to. Vote at least once. Vote soon and often. Okay, are we ready? All right, let's vote. Who thinks it's 1, D to the N? Nice and high so I can count them. That's 2, N to the D. Nice and high, please. D factorial by D minus N factorial. 3, 6. Number 4, N factorial by N minus D factorial. And V, 0. There are no functions that fit this. Yeah, this is the best voter turnout we've had so far. All right, the correct answer is there. Y. Why does it work this way? Yep. Good. We have n elements in A. Let's lay them out. Sorry, I put one too many blanks in there. Okay, so A1, A2, A3, AN. Each one of them has a map onto something, and there are D choices for each of them. So it's D, 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 okay, and we multiply, and that gives us D to the N. All right, written out as a sentence. First element of A maps to any of D. Of B, second element of A maps to any of D elements, and so on. Okay, so you scale all that up, and you're getting into the D. Sorry, T to the D. Okay, D choices apiece, yeah? Yeah. Yeah, how many different possible functions could you get that are different? Yeah. That's exactly what it's asking. All right, off to part B, yeah? Oh, sorry. Should be D plus 1 in this case. No, it can't map to nothing. So every element of A has to map onto something. And that's, I know that doesn't happen in calculus all the time because there can be holes in the real number line in the function, but here there are no holes. Everything's got to map onto something. Every ball's got to go into a thing. Okay, part B? Yeah, let's do part B. Okay, so the extra condition I've added here is that they're injective. Okay, so how many injective functions are possible? 30 seconds. Okay, you ready? All right, everyone looks ready? You look like, okay, when you hear your answer, that's the time, right? Okay. Okay, who thinks it's 1? Who thinks it's D to the N again? Nobody. Who thinks it's 2, N to the D? 2 of you. Who thinks it's 3, D factorial by D minus N factorial? 17. Who thinks it's 4, N factorial by N minus D factorial? A few more of you. And who thinks it's V, 0? Well, yeah, that's too many to count. All right. Okay. Let's first figure out something counting-wise, right? You take the first ball, same sort of blanks, and there are D choices, right? And then you take the second ball, and there have got to be D minus 1 choices, right? Because it can't go to the same place the first ball went. And then the next one goes to D minus 2 things, because it can't go to anywhere the first 2 balls went, and so on, until we get to AN. And the last ball will have D minus N plus 1 choices. And you multiply those all together, and it sort of looks like D factorial. There's a bunch of stuff missing. Okay, so the division of this D minus N factorial is the missing stuff. So that's we'll get to that a little bit later. Okay, but the answer is actually this, which most of you voted for. That's good. Why? Yep, you. N is greater than D. Yeah, N is greater than D. Okay, and remember, when you have N greater than D, right, you have more things in A than you do in B. Eventually you're going to run out of stuff in B that you can map onto uniquely, right? Okay, so the answer is 0. You actually can't do it. Okay, so this has a special name. Do you remember the name? I'll come right back to you. Do you remember the name? No? What's the name? Special name? No, it's not injective. Pigeonhole principle. Good. At least 2 things will map onto the same bin. Okay, so at least 2 elements of A will map to the same bin. Okay. A little tricky there, but yeah, if it was possible, okay, if N was less than or equal to D, you'd end up something like 3. Okay, so if you voted for 3, you're on the right track. Okay, good. All right, summary time. Okay, so this is just a bunch of the terminology that comes. So if f is a function from A to B, then we write f colon A arrow B. And f of little a is equal to B for some pre-image and image pair. The domain is A, the codomain is B, is the from and to set. A is a pre-image, and B is its corresponding image. Every A corresponds to a unique image, so it's got to map to something. It will not map onto 2 or more things. Okay, this is something also called a total function. And I don't want to get too bogged down in this, but it is slightly different than what you saw in calculus in high school. Okay, that's a real domain. We're doing something different here. Okay, so everything will map onto something uniquely. The range is a collection of all images, often written f of the domain. You can do f of any set, and it will collect all the images the pre-images in that set map onto. Surjective means the range is equal to codomain. Everything is touched in the codomain. Injective is anything that is touched is not touched more than once. And bijective is both. Okay, so we ended up having too many qualities that came as a result of this. The size of A is greater than or equal to B, the size of A is less than or equal to B, and the size of A is equal to B. And the fact that a bijective function gives you equality is a good thing. It allows you to connect two sets together and say that they're equal by counting them in two different ways. This is a combinatorial proof, and we did one of those. And it was maybe surprising. The sum of a bunch of chooses equals 2 to the 10. Okay, so that's your crash course in functions. Okay, and we will use a fair amount of that terminology as we go forward. Okay, any questions about this slide or any of the stuff from today so far? Yeah, feel okay? All right. The remainder of this unit and this week will be on combinatorics. Whoops, that's not the right one. That's my reference slide. Okay, and we have done some counting. I've sort of said some words about combinatorics already. Because it's useful when the distribution is uniform, we can just use combinatorics. We can make a counting argument as long as we're careful in our counting. Okay? The strategy is to count everything once and only once, and not spend like forever enumerating all the possibilities. Sometimes it's not possible. Sometimes the numbers are so huge, staggeringly huge, that you would never be able to list it out. Like even a computer wouldn't be able to do it. It's too many things. Okay, so you'd like to be as efficient as possible, and you will apply two rules. We've seen one rule already when we did sets, okay? And it is the rule of sum. Okay, so the rule of sum says that if you have two disjoint things that occur, if it's case A or case B, or A, events A and B is what I get. Anyway, if they're disjoint, then the total number of ways A or B could happen is the size of A plus the size of B. When you sound out the problem in your head, if you use the word or, then probably it's a rule of sum type of thing. Okay, so you should think about breaking it up into cases, or a bunch of cases. Maybe it's more than one. Like, so the rule generalizes to 3, 4, n cases as well. I only did A, B, C, but the number of ways A or B or C could is A plus B plus C. Now, there's a special case where subtraction comes into play, and we've seen how this goes for inclusion exclusion. Okay, that you can use subtraction to, as long as the overlap is easy to compute, you can subtract off the case where you overlapped and do it here. So it doesn't have to be disjoint in every case, and you can, again, extend this to 3 sets by using the inclusion exclusion for 3 sets. You need more information there, okay, so it might not be practical in every case. Okay, so we've seen this. It sort of drops right out of our accounting from set theory, sorry. I'm going to skip a slide. I'm going to keep it for Wednesday. The other rule is the rule of product. Okay, so it's adding or multiplying. Now, what does the rule of product tell you? It tells you that if you have two events that you're connecting with and, or sometimes and then. And we've seen examples of this already. We saw it with the functions, right? You map the first element onto one of D bins, and then you map on the second element onto one of D bins. Or even the second way we did it was D minus 1 bins, because we have only D minus 1 choices left. Okay, then these things scale multiplicatively. Okay, so you multiply the two sets of outcomes, m times n, or in the case where it generalizes, you've got k different events. Okay, k different events. Each one of them has its own number of outcomes, and as long as those outcomes stay the same number, no matter what other thing has been picked, then you're good. You can use the rule of product. Okay, and if we're using blanks, there's n1 ways of putting in the first thing from A1, N2, N3, and so on down to N sub k, and you multiply them together. Okay, so you end up getting a product. Okay, so it's going to be one of those two things in combination with each other, and we've seen some examples of that so far. Okay, of each. Okay, we are going to we're going to generate the other two generalizations. They have a lot of factorials in them. First thing on Wednesday. Okay, I don't have enough time to do that first example on page 27, but we're going to do that next. Okay, so hold that thought. We'll see you on Wednesday.